Once again, welcome to my YouTube channel, Pearson and Excel International Maths by Mr. Kamotho, and we continue to explain Pure Mathematics 3. You'll find all examples explained here, Pure Mathematics 1 to 4, and also International GCSE. Please follow and let's work together. In this video, I want to introduce to you example 7 of chapter 5 of Pure Mathematics 3. It's such a long example with a lot of literature, but I hope you are on page 111. I just want to make you understand what is it all about, because we will read together, but of course we are going to find out what is it that we are supposed to do. And we're told that the table below gives the rank by size and population of the UK's largest cities and district, and you find that London is ranked number 1, but has not been has been excluded as an outlier. Outlier is a number that is far away, far above or below the common data, because it doesn't conform with the formula that is obeyed or being used in that particular situation. We will see what is an outlier in statistics 1. Of course, Birmingham is ranked number 2, Leeds number 3, with this kind of population, of course, to two significant figures: 1,730,000, 620,000, 530,000, 480,000. And of course, we are told that the relationship between the rank and the population can be modeled by the formula P is equals to AR raised to power n, and that is where we are. The population is modeled by the formula P is equals to AR raised to power n, where P, of course, you can see is the population, and R is the other variable, which is the rank. Fine, where A and N are constants. Draw the table giving values of log R and log P to two decimal places. The two rows I've left here, they are to give the logarithm of R and the log of P. And you can see the log of R to two decimal places. The log of 2 is 0.301, but to two decimal places is going to simply be 0.3. The logarithm of 3 is 0.48 to two decimal places. You can verify that using the calculator. 0.48. The logarithm of 4 is 0.6021, but of course it's going to be to two decimal places, which is going to be 0.60. And the log of 5 is 0.7 to two decimal places, and the log of 6 is 0.78, again to two decimal places. But log P, the log of 1 million is 6. You can verify that using the calculator. The logarithm of 730, by the way, we can also verify that. The log of 730,000, so that we can exactly have a picture of what you're talking about, is going to be 5.8633, but of course to two decimal places is going to be 5.86. The other one follows the log of 620,000, 5.79. The other one is 5.72 and 5.68. That is part A, and we have just fulfilled that task of part A. Part B talks of plot a graph of log R against logarithm of P. Log R against logarithm of P. And with this kind of a question, we just have to come up with the XY axis, and let's say that this is the Y axis, and what I'm just drawing now is the X axis. And the graph of log R against log, or rather log P, plot the graph of log P, log R against log P. Log R against logarithm of P. And we need to know something. If we say this is going to be the logarithm of P, and this is the logarithm of R, we will have to verify the logarithm of P runs from 5.68 all the way to 6. So we may not have to start from 0, and that is an indication. So we can start from 5, 5.1, 5.2, 5.3, 5.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.9, and 6. We can talk about 5.1, 5.2, 5.3, 5.4, 0.5, 5.6, 5.7, 5.8, 5.9. We may have 6, and we may have 6.0, and so on and so forth. So what about the logarithm of R? The logarithm of R runs from 0.3 to 0.7. Again, 0.3 to 0.7 is what we should now plot on the x-axis. We should have 0.1, 0.2, 0.3, 4, 5, 6, 7, 8. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. And when we are talking about the logarithm of R as 0.3, what is the logarithm of P? This is 6. So this is 0.3 and 6 all the way there. The other one is 0.48, 5.86, 0.48, around there. And then we're talking about against 0.48 against 5.86, 48 against 5.86, somewhere there. A graph paper would really help you. 0.6 against 7.79, 5.79, 0.6 against 5.79, around there, and then 0.7 against 5.72, against 5.72, around there, and 0.78 against 5.68, and then you are expected to draw a line of best fit, meaning that we should now come up with a graph joining all these lines. Our graph talks about, it looks like something like that. That is our graph. And having said that, we could also be able to answer part C. Use your graph to estimate the values of A and N to two significant figures. Now, we have had the equation was the logarithm of P is equals to AR raised to power N. Introducing logs on both sides, you're going to have log P is equals to N log R plus the logarithm of A. You can see N is the gradient of the function. N being the gradient of the function, then log A is the y-intercept. It's going to be somewhere here, the y-intercept. So what is n? If we may want to calculate our value of n, we may have a triangle that looks like that. And with this, we are going to calculate the gradient, whereby the change in y over the change in x is going to give us the gradient. So n is the change in y, and you can just use the first log p, the last, and the first. That means 5.68 minus 6, because at this particular point y is 5.68, and in the beginning y was 6, all over, what is the value of y there, of r? The value of r now at the very last point is 0.78 minus 0.3. And what do we find here? What do we find here? This is going to be 5.68 minus 6 is negative 0.32 all over 0.48 all over 0.48, which is almost equals to negative 0.67. Negative 0.67. Let's see that. 5.68 minus 6 equals negative 0.32, and 0.78 minus 0.3 is 0.48. So negative 0.32 divided by 0.48 is around negative 0.67. So that is our value of n. If that is our value of n, then we know that n is equals to negative 0.67. And sure enough, you can see our line has a negative gradient. But what about a? What about a? Our value of a happens to be the y-intercept. And the y-intercept is going to be here. So this is 6.1 is going to be around 6.2. If you consult the graph, logarithm of a is actually the y-intercept, which is 6.2 or thereabout. If you draw accurately, you'll find something like that. That is not really important. What is important is to know how to evaluate the value of a. So if the logarithm of a is 6.2, it follows that a itself is 10 raised to power 6.2. How is this possible? How is this possible? Now, the vertical intercept, if the logarithm of a is 6.2, if the log of a is 6.2, there we are, shift log answer is going to be 6.2, and if we have logarithm of a to be 6.2, if we talk about shift logarithm of answer, we are going to have shift log answer in an attempt to get the anti-log using the calculator. It's simply going to give us the figure that we have in the display, 158,893 to two significant figures, 2, which is 1600000, and of course you will find that the y-intercept in an ideal situation, we are talking about 1.6 million. And therefore, this you must say to two significant figures so that you Do not ask yourself, why didn't I write the very accurate answers as I got it, 1584893 to two significant figures. So that is it. So you will be able to interpret such kind of questions using the knowledge that we've just understood. And it's simply about the antilog. Again, visit my YouTube channel, subscribe, and of course like and share the videos as much as possible so that we can understand mathematics together. All right.